Okay, so here we are again, CSIS 247 networking, and now this is lecture 8. We're going to look at the OSI layers. So this is found in chapter 7 on network reference models and standards. We're going to look mainly at the OSI layer model, and then also a little bit of the IEEE 802 or networking protocols. So the OSI network reference model is pretty much a standard. That is the standard that everybody sort of looks at for networking. The idea is that you have layers, and specifically there are 7 layers going from physical in the lowest layer to data link, network, transport layer at 4. Number 5 is session, number 6 is presentation, and at the very top is the application layer. So this was proposed by the International Organization for Standards. It's in French, so it ends up being ISO. So it's the ISO is the name of the Organization for Standards. They came out with the OSI, Open Systems Interconnection model for networking. The idea is that it provides a common way of thinking or a framework for software developers, hardware developers, and students of networking to work with and learn from for understanding networks. A couple of things to understand about the OSI model itself. It's not specific to any protocol suite. There's many protocol suites, but the most common one is TCP/IP, and TCP/IP sort of matches up with some of the layers, but not all. The OSI model is more complicated in some ways because it has 7 layers. So it's a 7-layer organization of how data travels from place to place on a network. The idea of using a layered approach is that all of networking is complicated. The software used to communicate with other machines is complicated, then all the networking stuff is also very complicated, and so what people decided a long time ago was to say that you should turn it into a series of interconnected tasks where each layer has some specific duties, and so when they communicate, the data sort of makes sense regardless of what protocol you use at each layer. And that's the big advantage. You can switch between protocols, and it's basically turned out to be a great success. That's how the internet runs, is basically on this OSI model, and it's worked really well. So it's one reason why it's worked really well is because of the structure. Each layer has very well defined functions, and it's actually, these are things that we do implement in software, in applications and in servers. So the function of each layer is to communicate and interact with layers immediately above and below it. So for example, we've seen how the transport layer interacts with the network layer below it, and then in OSI we'll see that it also communicates with or interacts with the layer above it, which is the session layer. And this is used a lot in web browsers, web servers, things like that. So if you want to look at how the OSI layers and the TCP/IP model line up, here are the OSI layers on the left, the 7 layers, and here are the layers of the TCP/IP suite. So one thing to note is that in the OSI layer we talk about physical layer, and that's things like media, cables, things like that. And then the data link layer is, you can think of that as the MAC address layer. And in TCP/IP we think of that as one layer called the network access layer. So that's a tiny bit different in that it's 2 layers in OSI and it's 1 layer in TCP/IP. And you might have heard that we call switches layer 2 switches, and so layer 2 refers to OSI layer 2, data link layer, where MAC addresses are used. Physical layer deals more with the actual cables and media, things like that. So layer 2 switches are data link or OSI layer 2 devices where they recognize MAC addresses. Layer 3 at OSI corresponds really well to IP, IPv4, IPv6. Those are two different protocols you can use. Also, there are things like ICMP, ARP. The one layer that maps very cleanly, I guess in addition to network, would be transport. So transport layer, the names are even the same thing. You have transport layer in OSI, and in TCP IP you have a transport layer as well. And you can choose between TCP, UDP. There's a couple other protocols too, but these are the main ones that we are worried about. And then on top of the transport layer, we talked about earlier how TCP IP has everything above it is called the application layer, but OSI splits it up, and it has turned out to be really useful, a useful way of thinking about how, for example, web applications or even websites interact with the server, web server, and web browser, things like that. Turns out there's a lot of stuff that happens at the session layer. And so if you were to look inside how web apps are implemented or web servers are implemented, there is actually code that's specific to the session layer, both for the browser and for the web server. So once again, there's slight differences between TCP IP and OSI. You should definitely, from now on, you want to be able to remember all 7 of these layers. That's really important. And also be good to remember the how these two models line up. You might want to start with transport. Transport layer is the cleanest. And then remember the ones below: network, data link, physical, and the ones above: session, presentation, and application. So just as with TCP IP, we looked at how some of these things show up in the properties of, let's say, your Ethernet connection in a Windows machine. You can also look at these as OSI layers. For example, you're going to connect using a device, a NIC, a network interface card. That is the physical and data link layers in OSI. You will have things like IPv4 and IPv6. That is the network layer and the transport layer. So this is for both TCP and for IP. So it's in both network and transport layers. And these things above it, these other protocols can be in either session, presentation, or application layers. Okay. So the idea of the OSI model is to sort of reduce the complexity. When you think of all the things that happen in a single device as you send packets across the network or receive packets from the other side of the network, there's a lot of things that happen. But an easy way to look at these things is, and we do that almost automatically when you think of like web traffic. Like when you look at a website, you have a top level or application layer web browser. It's running mostly here, but of course it's using all of these to get data from across the network. But when you use it, you're not aware of all of these layers below. You just think that you're talking directly to the server that serves out these web pages or web apps. And so that's the idea with these peer communication. You have this illusion that when you set up a web browser, you're talking directly to a web server on the other end, but actually you're only talking to the layer below, which is presentation, which talks to session, transport, network, data link, physical, and the actual data goes across the network through the media, be it the air for Wi-Fi or cables for Ethernet, eventually gets across to the web server, and those layers only talk to the layers above it. And then that's for data going up to the server. And then when data goes down, each layer talks only to the layer below, but the illusion is that you're talking directly from application layer in computer B directly to computer A application layer. but you guys know that there's a lot more to it than that. But this, if you can preserve this illusion and make it look like data that you send from computer A to presentation layer, that's the same data that shows up at computer B, going from its presentation layer to its application, then you know that things are working. So the idea is that you want to simplify the way you look at how these all this complexity is managed. So each layer on one computer behaves as if it were communicating with the same layer on the other computer. And so we call this peer communication between the layers. So remember that when you send data out, same thing with TCP/IP and the OSI model. When you send data out, it makes its way down the protocol stack. And so every time you go from one layer down to the next layer, you are sending units of data called protocol data units. And so layers may have their own formatting, a header usually, and at the very end, remember that in layer 2 you actually add a frame trailer as well. And then goes out on the physical layer on the media, reaches the receiving end, and when data arrives at the receiving end, it is passed up the protocol stack. So it works, all of this pretty much works the same way in OSI and in TCP/IP. Each layer in OSI reads its protocol data unit data, and so all we mean by that is in the transport layer we're talking segments, or we can also call it datagrams. At layer 3 or the IP layer, it is packets, and then at layer 2 it's frames, things like that. So in general we call these data units protocol data units, and it's different things at different layers. And so when you get data at the receiving end from the sender, each layer strips the header information, which is called de-encapsulation, that is, you're opening things up, and then passes that inner data to the next higher layer. And so data leaves the packet layer in a format, and then the receiving application can read the same format of data. So once again, just to emphasize, when you send data, you send it down the layers. So really, when you use a browser to send data to a server, you're not talking directly to the server. You're talking actually down to the next layers, eventually going all the way down as bits to the physical layer that's sent across the network. And then if you have a router, you actually end up in each router, you end up going up to the layer 3 and then back down the other side. We'll talk more about that later. But then the server, ultimately the server gets bits of data, which it then assembles into a frame, and then inside the frame is a packet, and then from inside that packet is a segment that you take out, and that segment is the protocol data unit for transport layer. And then out of that segment comes data for the session and presentation and application layers. So at the receiving end, your data is passed up the protocol stack. Okay, so let's take a quick look at these various layers, starting with the top layer, application layer. It provides interfaces for applications to access network services, for example, file sharing. If you want to send messages or database access, these are all things that happen at layer 7. And right above, actually, the application layer is the actual applications themselves. So a web browser, technically speaking, it sits above layer 7. And usually you'll have a client component like a browser talking to the application layer on the client, and so that's the client component. And then at the other end, on the server side, you have server-side application layer talking to the actual web server software. So protocols that you use at layer 7 include HTTP, and HTTP and HTTPS are used interchangeably. FTP is file transfer protocol, SMB is session message block, I believe, and then TFTP is trivial file transfer protocol. SMTP is for mail, simple mail transfer protocol. So there's a whole bunch of protocols. The most common ones are HTTP and FTP probably. So possible problems at this layer include missing or misconfigured client or server software that can cause all kinds of problems with data being sent or received. You can have incompatible or obsolete commands used to communicate between the client and the server. There's problems that can happen at this layer, and usually it's software problems. Next layer down below the application layer is the presentation layer. That's layer 6. It handles data formatting and translation. So for outgoing messages, when you're sending things down, it converts data from the application layer into when you send it down, you get data from the application layer that you convert into the certain kind of format, and then you pass that down to the session layer. Incoming messages, it's the opposite, and so you're getting things from the session layer and you're going to pass that up to the application layer depending on how the application layer expects the format to be. So there are all kinds of software that's used in presentation layer. There's a component called the redirector, and what that does is it intercepts requests for service from a computer, and then requests that can't be handled locally are redirected across the network to a network resource that can handle that request. So it's just an example of one kind of software that runs at this presentation layer. Below the presentation layer is the session layer, or layer 5. This is what allows two computers to hold an ongoing communication. It's like a chat. It's like you're sending a message and then expecting a response, and that's considered like a session. And of course you can break off a session. That is when you, for example, stop sending messages to your friend and then you start up again later. That's a new session. So there's a lot of setup involved in setting up these sessions, but then once you set it up, the session layer is what keeps track of time. So this layer also handles communication setup ahead of the data transfers, and then session teardowns. That is, you're saying, okay, I'm done with this session when the session ends. Common network functions at this layer: name lookup, domain name system lookup, log on and log off when you log in remotely to another machine, like for example remote desktop protocol. That is handled, the actual process of logging in and logging off is handled at the session layer. This layer manages the mechanics of ongoing conversations, such as identifying which side is transmitting and for how long, things like that. Things like checkpointing is performed at this layer, for example, to keep audio in sync with video. For example, audio is very fast and very small, whereas video is much larger. There's a lot more data, and so often what happens is audio gets to a destination faster than the video, because video is just plain bigger. And so some checkpointing has to be done so that you sync up the audio with the video. Otherwise, every once in a while you've probably seen that the audio just is not matched up with the video. That's because this syncing sort of is not working. So this is something that happens in the session layer typically. Okay, so next up is the transport layer, layer 4. This we've seen a whole lot of in TCP/IP, because that's the T in transport TCP, the TCP layer. So the transport layer manages data from an application, and on the so there's data coming in from the upper layer, session layer, which gets data ultimately from the application and then sends it down. And so one thing it has to do is remember that if you use TCP, transmission control protocol, you have to send data and make sure that it reaches the destination reliably. And you can't send, for example, a massive image all in one piece. You have to break it up into smaller chunks, and these we will call segments. Some people also call it datagrams, but for just to be consistent, we'll call them segments. And so if you have, for example, in the application, presentation, or session layers, a whole lot of data representing, let's say, a big image, at the transport layer, you break it down into much smaller chunks, and then you add on a header for the transport layer, like TCP header for the first segment. And then you do the same thing. You take a next chunk of data from here, put that into segment 2. You actually number them, and then take the last, let's say the last layer, the last chunk of data from the session layer, put that into segment 3, and so on. And then you send each one of these separately. This segment will go into a packet, which will go into a frame, get sent out on the network. And then the thing is to reassemble these so that you have the original data faithfully reproduced at the destination. You have to know the segment number so that you can put the data together in the right order. So that's really important. And it's the transport layer that manages the ordering on both the sending side and the receiving side. On the receiving side, you have to make sure you got 1, 2, and 3, and only then can you put them all together. So segmenting data is important. Every network technology does have what's called a maximum frame size or a maximum transmission unit. It's usually like in 1,000 bytes or so, although there are ways that you can use what are called jumbo frames and transmit large amounts of data in one chunk. So most of the time this maximum transmission unit is well defined, and that sort of determines the overall rate at which you can send data. You use flow control acknowledgements for reliability. That is, you don't send out, if you have 1,000,000 segments to send out, you don't send out all 1,000,000 at a time. You send out a small window of maybe 10 or 20, and then wait till they're all received reliably, and then only then when they're all received do you send the next set of 10 or 20 or whatever. And at the receiving end, these segments have to be resequenced, that is, assembled back into the original data that was sent out from the sender. Okay, so in the transport layer, once again, you have the session layer protocol data unit, which is just called, in this case we'll just call it data, and then we put that into a segment with a transport layer header, let's say a TCP header or UDP header, and this whole thing is called the transport layer protocol data unit, which has the name, which we call segment. We'll call it segment, although if you look online, not everyone's consistent about this. Some people call it datagram and also some of the other things, but to reduce the any kind of confusion, we'll call things that happen at transport layer segments. That's the protocol data unit name. The key fields that go into the transport layer header are source and destination port numbers, sequence and acknowledgement numbers, and the window size. The window size is telling the receiver, I'm sending number 1 of a window of 10 segments, and so tell me when you get all 10, I'll send you the next window of 10 or 20 or whatever. It turns out, although here it only lists source and destination port numbers, you actually do list the IP addresses too, but this is the main thing. This is what determines. So the source port number tells is an indication of which program on the source computer is sending this segment, and the destination port number signifies which application on the destination computer is expecting to get this segment. So for example, regular HTTP uses port number 80, and so all that really means is that it is going to be the web server that gets this message, this segment, coming in on port number 80. So some of the problems that happen at this layer include segments that are too large for the medium. So you might have a MTU, or maximum transmission unit, that's much smaller than you expect, and then you might have to ditch it and then retransmit with a smaller segment. So there might be mismatches, but those things usually are handled by the transport layer. And so what you would have to do is one thing you can do is force the layer below, the network layer, to fragment the segments, and that is usually it causes unexpected performance degradation. You can also do this at the transport layer as well, but you cannot foresee what the maximum transmission unit size is, and so sometimes you do have to rely on the network layer to break that segment up into smaller pieces, and resulting in slower than expected transmission. Okay, so we'll take a break here and then move on to the layer below, which is the network layer next.